Hi folks. So last time we were talking about combinational logic, and we developed some Boolean algebra using simple gates. We did some simplification and we implemented that logic. And you may recall that we ended up with statements like these, where we were using sum of products or product of sums to derive an output based on some digital inputs. And so we used the example of a lock. It wasn't a very good lock. In fact, it was a terrible lock. But it still showed you how we took those buttons, the B inputs here, and mapped them to an output, the Y, which was whether or not we wanted the lock to open or not. So that was an example of a static system. And that was part of the problem with the lock, as you recall, was that you had to press everything at the same time. But what if you wanted to have a dynamic system? Well, as we mentioned last time, the dynamic systems come about from sequential logic. And so we want to look at the difference between our combinational logic and our sequential logic, which comes from our memory devices. And we want to build up sequential logic in the form of finite state machines. So finite state machines are how we're going to do our sequential logic. And we will, after we've got our finite state machines, we'll be able to do some state reduction to simplify them for implementation, although it's not required. And frankly, on the Arduinos, it's not always necessary or interesting to do, but you should know how to do it just in case you end up with a really massive state machine that can be reduced easily. So once we've got our finite state machines, there's some case studies that I'll post that are not solved. I don't have solutions written out, but certainly you can work through them. There are many possible solutions. So let's think about a general mechatronic system. You have a system, and it is interacting with the environment. The interaction with the environment, the system is going to take some sort of input through a sensor. It's going to act on it in some way through a control system, and it's going to respond to the environment in some way through an actuator. Now, it doesn't matter today what those sensors and actuators are, but we want to figure out how do we do this mapping from the inputs read by the sensor to the outputs generated by the actuator. We need something to go in that control block. What in the world goes in that control block? Well, we need a way to develop an appropriate logic for the control block. And, you know, because we're talking about sequential logic, you know that we're going to put a finite state machine in there, but we're going to get to that part. So we need a way to develop an appropriate logic to interact with the environment. So how are we going to do that? Well, it kind of depends on what you're dealing with. So let's consider this particular robot. This is a PackBot. So this particular robot, you can see it has a camera system up here. It's useful for inspections. It's useful for bomb disposal applications. It's a remote controlled sort of thing. So in this particular robot, you can see from the diagram on the right that it's going to drive forwards, it's going to have some flippers, it's going to have some motion with the flippers and the drive going at the same time. So how do we classify these sorts of control? Well, if what you really care about is that camera, and you want to talk about how the camera moves through space, you know, what kind of path does it follow through space? How fast does it go through space? How does it avoid obstacles? That's trajectory planning, and that is what I would be considering component level control. So if you've taken any dynamic systems and controls class in the past, you have talked about trajectories, you've talked about transfer functions and state space. That is component level control. But that's not really what we want to do in this class. You're doing that in other classes, but that's not what we want to talk about. We want to talk about this other diagram. What happens when we have these tasks that we want to cover? You know, we want to drive forwards for a while, and then we want to rotate something. We want to look around. Those are higher level tasks, and so I'm going to call that supervisory level control. So supervisor control is different from component level control. The components, obviously, we move things around. The supervisory says what should be moved around. This is not necessarily the same terminology you'll see everywhere else. This is the terminology we're using in this course. So, if we're focused on supervisory control, what's it going to look like? Well, so we're going to deal with finite state machines. Finite in the sense that there's only a finite number of these states. Fun point, I saw an article asking, you know, what is an infinite state machine? Well, that particular author claimed that the only infinite state machine is the universe. So everything else we're dealing with is finite state machines. So in this particular PackBot example, you can see from the diagram that it's going to drive forwards. At some point, it needs to get over an obstacle, so it's going to stop driving forwards and it's going to rotate the flippers. And then when it gets to a certain point, it's going to start driving forwards while moving the flippers. And so you can see those are three different cases, and those three different cases are all happening in a sequence. And not only are they happening in a sequence, the robot is in one of those cases, and then it moves to the next case. These are separate cases, it's no mixing of them. And so I've drawn those out here as blocks. And so you can see that the blocks are denoted here. And instead of talking about actuators, these are just concepts. We'll get a little more specific later. And so there's the drive forward case, there's the flippers rotate case, and there's the drive forward with flippers case. We might call these states. Now, I haven't explicitly defined the states, I haven't explicitly defined the inputs and the outputs, we don't know what is causing the transition, but you can see that the robot is in one of these states at a time. And that's how the finite state machine is going to work. The robot is always going to be in one state at a time. And it's going to transition from one state to another state, and the states in this case are defined by the outputs. What is happening, and then how do I move from this case with this set of things happening to another case with a different set of things happening. So that's the general idea. We're going to develop state machines, finite number of states, and they're going to describe the motion that we want to see from our robots. So it's a declarative model versus, it's not an imperative model, that's the alternative. So a declarative model declares what is it you want versus imperative is how you're going to get there. So it's a declarative model with a finite number of states. I already mentioned that part. You can only have your finite state machine be in one state at a time. Now, I keep emphasizing that because it keeps coming up as a source of confusion. But your robot, your finite state machine is going to be in one state at a time. And it's going to move between the states through these transitions. Those were the arrows on the diagram. And those transitions occur as a function of the inputs. So how do we define it? There's a set of states, and there are conditions under which the transitions occur. So what are the conditions that cause you to move from state A to state B? Define the states, define the transitions. And so how are we going to describe this in a way that everybody else understands it? We're going to use state transition diagrams, and we're going to use state transition tables. And we're going to cover both of those. You're going to see a lot of those. So where does it come from? It comes from sequential logic. So it looks a little like this, where we've got inputs on the left and outputs on the right. You can see that we've got a couple of different blocks here. We've got what's called the next state logic. So we know what state we're in. We're going to use the inputs and combine that with the states to generate the next state. And we're going to use the next state into our memory device, and we will take that memory and we'll use that to hold the state, and we will combine. Now, there's different ways to do this. This isn't the only diagram that works. We're going to, in our case, mostly use what's called a MRE machine, where the output logic is only going to depend on the state. So that's why there's just these going into it. And again, the output logic will generate the outputs. Sometimes you'll see the inputs going into the output logic, and so the output logic will be a function of both the states and the input logic, and we'll define that later. And we'll also take that state and we'll feed it back so that we can use it in the next state. So notice that there's a key word here. The next state is combinational logic, and the output is combinational logic. Hey, you know combinational logic. You're an expert on combinational logic. Okay, expert might be too strong, but you are at least familiar with combinational logic. So if you can do combinational logic, then you can already figure out your next state logic, and you can already figure out your output logic. So the thing that we're missing is in the middle, is the current state being held through a memory device and the feedback. And so now we're just going to add to what you're already doing, wrap the whole thing up as sequential logic, and we'll use that to define our finite state machines. So we might write it out like this. Q is the state, and so Q star is the next state. So the next state, Q star, is a function of the current state, Q, and the inputs. And the output, Y, is a different function of the current state, Q, and the inputs. Now, you might have seen something like this before. It looks a lot like our digital control, where the next state vector is a function of the current state vector and the current input vector, and the output is also a different function of the current state vector and the input vector. Looks very similar. So notice that what we're ending up with is an output that depends on the current and all the past inputs, and that we have this history dependence. And so this is a not a static system like we were dealing with in combinational logic. This is a dynamic system. and it's achieved through that memory device. So where do we go from here? We need the memory devices. We need to add those into what we already know, the combinational logic. So we need to be able to talk about memory devices. So the next thing we're going to do is we're going to start talking through memory devices, and then we will use our memory devices to build up finite state machines. So next video.